Okay, so let's take a look at these, and I'm going to write what all the groups have done together. If all 5 groups say it's false, I'm going to assume it's false. Okay, so everybody said the first one is false, and people wrote that this is, you can, like on a quiz or a test, I just want to point this out. I'll ask you if something's true or false, and you have to change the sentence to make it true. The easiest way, if you're listening, please, the easiest way to show that in this case this isn't true is to go like that. It seems like it's a cop-out, but it's true. That is now a true statement. So you've made it true. A lot of times students will feel a little more obligated, even though you don't have to, and actually write in the right answer. Like in this case, when you multiply exponentials, you add the exponents. Your exponent properties should be available to you. So if they're not, please review section P2 in your book. P stands for prerequisite skills, which means everything in chapter P is something you should have come into this class with knowledge of. Doesn't mean it's right there at the top of your brain, because it could have been a while since you had it, but every one of you is in a totally different spot, so review as needed. If you just took Math 096, for example, you may not need to review. I had a person in my first class who hasn't had math since the 9th grade. It's been like 4 or 5 years for that person. So that person needs to review a little more. Okay, so everybody's different, and I recognize that. What do we have for 2 all the way across? I see all trues. I'm going to assume it's true. It is true, by the way. 3, what do we have? We have false, 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 false. So that is a correct statement that whenever you add or subtract, there's a golden rule in mathematics. When you add and subtract, you have to add and subtract like things. They've got to be like. These are called like radicals because they're square roots of 2. So all you're saying is, how many of these square roots of 2 do I have? I have 31 square roots of 2 and 10 of them. So altogether, 21 and 10. I've got 31 of them. Okay, so that's how you could have changed it. 4, what do I have? False, false with no answer, false with an answer that's different than table 1. 4 says table 5 says it's true, and table 4 says it's false. So notice all the different answers here. Not only do we have some people thinking that this is true when it's false, I'll at least start with that, but also some people said it was false but have a different answer than tables, what were they? Tables 2 and 4. So this is one of those things in mathematics that kind of mess with you for a while until you kind of get the hang of it. There's a couple of things going on here, why you get this mixed up. Let me tell you what this is called. You'll never hear me say this guy and that guy. I use mathematical language and so that you can understand what things are called. This is called a binomial squared. Binomial squared. Bi means 2 terms. Binomial means 2 terms. How do you get terms? They're the parts of an addition or subtraction problem. So if you look inside the parentheses, you have 2 separate terms separated by subtraction. You also see an exponent. So what do students do? They go, oh, I can just square each one of them and I'm done. It seems logical and reasonable. Why? Because you're used to doing things like this. And you square each one of them. So why can't you square each one of those? Come on, why make up new rules? Well, this property, 3nm squared, is an exponent property because exponents apply to multiplication, because that's what exponents are, a short way to do multiplication, and division, because division can be rewritten as multiplication, right, by the reciprocal of the denominator. Exponent properties apply to multiplication and division only. This is subtraction, totally different ballgame. The only part of exponent you apply is what it means to square something, which means you multiply the base here, which is all that stuff in parentheses, times itself. So this is 4x squared minus 1 times 4x squared minus 1. I will keep reminding you about this property throughout the semester, because the last thing any of us want is a Math 107 student leaving and squaring this by calling it 16x to the 4th plus 1. Okay, so once you square this out, meaning you duplicate it twice, right, with a multiplication in between, you then use your distributive property twice. And that gives you 16x to the 4th minus 8x squared, because your middle term and your outer term are duplicates of each other. Negative 4x squared and negative 4x squared give you negative 8x squared, and then you have your plus 1. So notice you get those two that you always think it is, but you've got that darn middle term you got to remember. Okay? That's a biggie. That's one that we often forget. Okay? Questions on that before we move on? All right, so let's go back to our table and see where we're heading. 5, what do we have? True, false, true, 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 false. Table 2, what did you have instead? It is true. So let me help you with wherever you thought why it was false. What part of it did you think was false? Oh, you weren't sure? So you just made a guess? All right. So 24 divided by negative 2 is negative 12, and that takes care of that right there with the dash out front. And then you have y squared over y to the 5th times x squared over x to the 5th, y to the 13th over y to the negative 2. So x squared over x to the 5th, what's your exponent rule tell you to do with the exponents when you're dividing with the same base? What do you do to the exponents? You keep the base the same and what? Subtract. So that's x to the negative 3, which says put it downstairs. And then you have y to the 13th, take away a negative 2 is y to the 15th. So that is true. Again, exponents are covered in P2 and P3. 6, did we all end up doing all right with 6? We got a false up there, but no answer. A false up there with almost an answer. 1 take away a quarter is 3/4. We've got a false up there with no answer, a false up there with 3/4. And I want to talk about, and I'm really glad Table 4 did this, because I often forget to talk about this. And it's really important. So anything raised to the 0 power, except the number 0, which is undefined, 0 to the 0. Any number raised to the 0 power, anything except 0, is defined. Defined. This is how it's defined. It's not going to be intuitive. It's defined to be 1. So the first term there is a 1. The second term has a heck of a lot going on with it. And this particular thing, this bugaboo bugs students every semester. I'm going to cover a problem very similar to this in the demo, so I'm going to save my discussion for the demo. However, I want you to notice what Table 4 did, and I'm really happy they did this. They remembered that that dash, when it applies to an exponent, has something to do with inverting and changing position. That's good, because there's a part of that that's still in their memory bank. However, you never, ever change the exponent itself. They inverted the exponent. Not only did they invert it, but they changed its sign. Okay, so that dash, everything you see up here in that fractional exponent applies to your base, the thing being raised, the 32. It doesn't apply to the actual exponent itself. It applies to the base. Everything goes to the base. So I will cover something similar to this, and if you couldn't finish this off, you should be able to finish it after I do an explanation. Okay, I'm going to just save it instead of being repetitive. All right, 7, everybody has true for 7, and that is true. 8, we have a true, a false, which I think was a guess, if I remember correctly, right, Paul? was a guess. I shouldn't just be picking on you. It's just because I know your name. I'm not picking either. 8 is true. Oh, we got a false there, and we've got 3 falses. This is actually true. Part of the problem is you often see the property for radicals, which is also the exponent property, a product to a power, just written as an exponent instead of radicals. Those say exactly the same thing. That equal sign goes both ways. So often you start with a product like the square root of 300 and you decide how to break it out. This isn't really done to help you very much. So some students might start by doing this. Square root of 25 is 5, and 25 times 2 would give me 50. So that they start there. Then what do you do with this? Well, then you'd have to break this up to the square root of 3 times the square root of 2. And then you'd have to know the square root of 2 times the square root of 2 is 2. And that gives you 10 square roots of 3. That's awful. Yuck. Right? That's really going to mess with your brain. So, square root of 2 squared, the square and the square root undo each other. Okay? So, why not squish it back together, because you can go both ways here and start fresh. And this is what in Math 096 students have a lot of difficulty with. Just because someone presented you with it as a square root of 50 times the square root of 6, you don't have to like that separation. So if you go back to the beginning, and now you ask yourself, what's the biggest square root that's what's the biggest perfect square that's a factor of 300? You know it's 100. Because 100 divides into 300 evenly. So you can write it like this. Now that's a lot easier to look at, a lot easier to simplify. Okay. All right, the next one, I believe every single person around the room, almost, no, everyone said it was false with the right answer. Yay! We don't have to discuss that. 10, what do we have? True, 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 true. And it is true, yay. And then the last one, false, 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 and everybody has the correct answer, almost. What do we have over there? X plus what? Oh, X plus 5 doesn't equal, right. So this is equal to X plus 5. That's correct. Okay. So let's do a little bit of a demo, and then I want to get you started with your exercises. Did you need more of that, Olivia?
Wait, what? You wrote for 11, it was true.
Did I write true for 11? It's false. Yes, it's definitely. If I changed it, I made a boo-boo. Yeah, it's false. Thanks. Anything else before I scoot over to the demo? All right. All right, let's talk about B. Let's talk about C and D. I'm going to leave A. I'm going to leave. You can look that up in your book. But B, C, and D need a little discussion. I'm going to try to keep it to 5 minutes. Please stop me if you don't understand. Okay, I'm going to try to do it fast because it's review. I don't normally go this fast, but please stop me. 8 to the negative 2/3 power. There's 3 things happening here. 3 things that's happening to 8. 3 tasks you must perform in any order. Although some orders are a little easier to do than others. You have to take care of this little thing at some point, which means to change the position of the base, or invert, or reciprocal, whatever works for you. Of base. What's the base here? What's the base of this x? The 8, right. The base is 8. The exponent is what we call a rational or fractional exponent. It's negative 2/5. The numerator 2 acts as it always acts. It says square something, square the base. The denominator 5, my little memory device for this, the denominator is the cellar. When we harvest our root vegetables, most of us are not living with agricultural farming families anymore, but most people 20, 30, 40 years ago knew that root vegetables go in the cellar. There was actually a part of most homes that were family farms that had a root cellar. It's dark, it's cool. Your roots go in the cellar. Yeah? Oh, okay. Am I confusing that with the other problem? Yeah, it's a 3. Thank you. So that tells you, just remember, roots in cellar. That tells you you're taking the cubed root of the base. That's what that tells you, what root to take. Now, which order you do has absolutely no bearing on the problem, because that particular problem can be written like this. Because when you have a number raised to a bunch of powers, you multiply, that's negative 2/3. Negative 1 times 2 is negative 2 times a third is negative 2/3. You could write it like this if you wanted. 8 squared, then invert it, and then take the cubed root. You could do it this way. Take the cubed root first, then square it, and then invert it. Doesn't matter which order, because this is all multiplication, and the order of multiplication doesn't matter. So what do I usually do? If the base is a whole number instead of a fraction, I usually try to make that number as small as possible. So I usually start with the root. That's what I do first. So I take the cubed root of 8, and that gives me a 2. I've done that part. So now this is equal to 2 to the negative 2, because I've taken that cubed root. Then I usually apply my numerator of my fraction. I square it. And that leaves me with a dash up there. What number comes after that dash? 1. And then I change the position. 4 over 1 becomes 1 over 4. That's usually the order I do it. If it was 1/8 to begin with, I would have started with the position change and made it 8. And then I would have done the root and then the square. The numerator is always the middle step for me, always. And the first and third step here can interchange based on whether you have a whole number for a base or a fraction. It's really up to you. You can do it in any order. You could square 8 first and get 64. Then you could take the cubed root and get 4. And then you can invert it and get 1/4. Okay, it doesn't matter. Just depends on where your mental math skills are in terms of knowing your powers and stuff like that. Questions on rational exponents? Yep. Jesse? Yep. I did the squaring. I squared the 2, I got 4. And then I have that negative left. And then that says, take that 4 and put it downstairs. Okay. The negative 1? Because I could write 8 to the negative 2/3 like this if I wanted to. 8 to the negative 1 times 2/3, right? Okay. So that little dash is it's like a hidden one. Yep. Okay. Other questions? All right. So factoring, P5. Most of you need to spend a lot of time on P5. For some reason, I don't know why, factoring skills tend to be one of the weaker prerequisite skills. People don't like factoring, and I don't quite understand it because I love it. I don't know, maybe that just makes me weird. I don't know. Number 1, do you understand what factor means? That's the first thing. Again, I will not say you have 2 guys here. You have 2 terms here. 5x cubed and negative 45x. Those are your 2 terms. This is a subtraction problem. The factor means to take that subtraction problem. This is a verb. Take that subtraction problem and turn it into a multiplication problem that's equivalent. Because you want to create factors, not terms. That's what it means to factor. All right. So the first factoring technique that we always forget and is probably one of the most critical is finding the greatest common factor. In fact, when I used to teach Math 096 and we were doing factoring and everything after factoring, I'd have my students literally write GCF on their palm or on the back of their hand, wherever they would remember to look. And I would tell them when the test day came, put GCF right there, don't forget it. So you look at each term and you say, what is common as a factor to each term? 5 divides 5, 5 divides 45. So 5 is a common factor to each term. And each term contains at most 1x. So 5x is the greatest common factor. So the first form of factoring is 5x. You have two terms separated by subtraction, so you must put two numbers in there, or two variable expressions, or two expressions. And often, why do I say that? Because sometimes when the greatest common factor is identical to one of these, you forget to put it back in as a 1 in that slot. So this is 5x times x squared minus 9. And you're usually happy with yourself and you say, that's enough. No, because this is what we call a prime factor. Can't be factored any further. 5 is prime and x is prime. We don't even know what x is, but we call it prime. Can't factor it. However, this is not prime. Yep. What's your memory say, Jesse? X minus 3. Yeah. These are kind of the fun ones to factor because you have no middle term. X squared is a perfect square and 9 is a perfect square. So it's x take away 3 and x plus 3. It's the negative 3x and the plus 3x that give you the 0 in the middle. So this is now what we call completely factored into 3 prime factors. Notice something. This doesn't always work, but often when you have this is called a polynomial or a binomial. Notice the highest power is 3 and you have 3 prime factors. All right. The last one is the most difficult, and clearly we're not going to have time to do this. However, you see what this first says? This is a long activity and a lot of material to view. We didn't even start it today. Work on it at home. You've got a week or so to do it. Every class you come in, I'll check this out with you. If you have any problems, I'll go through it with you. If you have problems, see me during my office hours or go to the studio. I want to take some time to talk about the very last one. All right, we're adding. What's the golden rule in mathematics? To add, they must be like. Yes. In this case, they're like fractions. In our preview activity, they were like radicals. When we add numbers, we add like place values. So what I want you to see here, and I often do this with students, I say anytime you have more than one term, put it in parentheses to help you see that as two totally different things. So in your mind, I just want you to think for 1 minute. Let's, in your mind, let x equals 7. So on the top, we would have 21, and on bottom, we would, oh, I don't want it to be 7. Let's make it 5. So on the top, we would have 15, and on the bottom, we would have 7. Yeah? And the next one would be 5 if x was 5, and the bottom would be 5 take away 2, which is 3. Okay, so before we get to the arithmetic version of it, let's look at the algebra. Can you factor x plus 2? Is there a common factor to anything other than 1? No. We call this prime. This is totally different. X minus 2, it's prime. To find the lowest common denominator for those two, whenever you have prime factors, what must be the smallest common multiple of 7 and 3? What would you do to 7 and 3 to get the smallest multiple? You just multiply them. 7, 14, 21. 3 is never going to have a 14. These are prime. The smallest multiple is just to multiply them. You like those, all right? So the smallest common multiple, or the smallest common denominator, the least common denominator here, is just the product of those two particular prime denominators. Okay? They don't have anything in common, so there's no end of the story. That's it. You just multiply them. That's the kind you like. Okay. Now we have to change each one of those fractions. This is kind of a pain in the butt, but it works. I'm going to make these two denominators two different colors so that visually it might be appealing to you. I'll keep the numerators the same color. Maybe I should keep them blue. All right. I like working with colors. We want to change each of these fractions to what we call an equivalent fraction, exactly the same. But now with this new denominator, if I had sevenths, I'd change it to 21st by multiplying top and bottom by 3/3, which is 1. If I had thirds, I'd multiply it by the number 1 in the form of 7/7. So what I'm going to do here is I'm going to take this fraction and I'm going to write it as an equivalent fraction that has this as the denominator right here, the green factor and the red factor. What factor is missing from the first fraction? What color on the denominator is missing? No, that's the numerator. Yeah, the denominator. What color is missing? If they both have green. Try again. Red, yay, red. The x minus 2 is missing. Mathematically, you have no right to multiply anything by a number except for 1 if you want it to stay the same. So the form of 1 we're using is x minus 2 over x minus 2. So this first fraction becomes 3x times x minus 2. And this is where I deviate a little bit from other teachers. I just write LCD there. And the reason I do that, I'll show you in a second once you get it written down. I see students do all this work and then they go like that and they're right back to where they started. I know it's awful, like my heart cries for them. All right, so that's why I use LCD, because then you don't have that temptation, right? So what are we going to multiply this x by top and bottom? X plus 2, right? Say it out loud, shout. You're happy. Yes, I know what to say. Yes, even if I didn't, it's all right. Oh, that should be blue. Oh, come on, blue. Times what? X plus 2. And then it's all over the LCD. They're like now, you have the common denominator, put it there with one fraction bar. And what do you have? 3x squared minus 6x plus x squared plus 2x. That gives you 4x squared minus 4x. Now throw the denominator in, x plus 2, x minus 2. Do not multiply it out, because then you might cancel terms and we're really not happy. The only time you can reduce this is if you can factor it, and one of those factors looks like that. Then you can reduce it because you can divide by 1. You don't have an x plus 2 on top or an x minus 2. Okay. This is the end of Math 096, and it's the part that messes with your brains the most. This is P6. You may need to review some of that. Okay. Now, yep, go ahead, Olivia. You can't. You can. If you pull out a 4x, you get this, x minus 1 over x plus 2, but there's no common factors. See, there's no common factors to reduce it. You could write it like that.
In the bottom, when you
Multiply it out.
multiply it out, wouldn't it be x squared minus?
Yes. No, but then it's not factors. It's got the subtraction in between it. That's called canceling terms, and we can't do that because the x squared minus 4 belongs to both things on top. Okay. All right. So when am I going to see you? Monday. What are you going to absolutely try to do by Monday? Huh? The activity, some of it, but make sure you get onto my math lab, get your access code, get set up so you're a happy camper, okay? If you have not signed up for one of those appointments, if you came in late, I'd like you to do that. The appointment sheet's over here. All right.